Hi, Kevin.
Hi, Dr.
Hi,
Wheeler.
Lyle.
And
How you guys
Lyle.
doing?
Pretty good.
All right.
Yeah, things are going okay.
Good to hear it. Good to hear
Hey,
it.
I do have a question. I should have
Yeah.
asked it at the end of last quantum, but the
That's okay.
summation of the symmetric and anti-symmetric parts and it being equal to the metric, is there any chance maybe at the end of lecture today we could briefly, you brought it up when you were talking about the Dirac equation?
Oh, the symmetric. Yeah. Here, let me show you what I'm talking about there.
I've seen that before. I just haven't sat down and worked it out for myself, so I'm always a bit confused whenever I see that part come up.
All right. So the summation of the trace of the product of a symmetric and an anti-symmetric thing vanishes. And let's just prove it. And I have to pause to let some people in here. Let's see. Yeah. There it
Don't
comes.
forget they're not as important as I am.
The what?
Nothing, I was just joking. Never mind.
Oh, sorry. Like a good joke. Okay, so suppose we have a symmetric thing with an anti-symmetric thing. So we can remember. So, this is equal to minus S mu nu A mu mu, right? And well, there comes Alex. And because this is symmetric, I can write this as S nu mu A mu mu. And now I can rename dummy indices. So I'm going to call nu mu, and I'm going to call mu nu. Same thing. But now this thing's equal to minus itself, so it's 0.
Okay.
So, So yeah, you can think of this as, well, if I flip that pair of indices, that would be the trace of the product of the two. But anytime you fully contract a symmetric thing and an anti-symmetric thing, you get 0. So in the case of the gamma matrices, we had gamma mu, gamma nu times a mixed partial. And the mixed partial is symmetric. All right, that's an outer product of things. That's some matrix. It's a matrix of matrices, but never mind that. I can always write that as a symmetric part plus an anti-symmetric part. So just the product, 1/2 gamma mu, gamma nu, minus gamma nu, gamma mu. And now, if I contract this like this on a symmetric thing, our theorem shows that this is going to vanish. So that says that gamma mu, gamma nu, d squared, dx mu, dx nu is going to be just the symmetric part on the, let's just call this mu nu. Yeah, you know what that is. Okay, so this is all that survives that contraction. So it's this that has to be the metric.
Okay, that's
Okay.
perfect.
Eli, Alex, hello, Guillermo. Good to see you guys. How are we doing?
Hello there. I got a question from the last class.
Yes.
And I didn't ask it because
yes.
I didn't ask it because it was I didn't think it might be appropriate. But the phase symmetry that you brought up was a global symmetry, and I was wondering, as like if you can do basically a local symmetry of
Yes.
U1, and I was wondering like if that's difficult at all.
It's not difficult. It's a straightforward gauging. So if you're familiar with gauge theory, that's one of the easiest ones to do. Where it works best is if you do it to the Pauli equation, because there you actually derive the coupling of the spin to the magnetic field. It works out just right. It's basically giving you minimal coupling to the the electromagnetic field. So yes, you do gauge that U1 and you do get very useful information. Yeah,
Looks like Eli got dropped.
Sorry, what?
Looks like Eli got dropped again.
Oh, rats. All right, well, he was able to just log back in last time. Yeah, okay, I hope he'll be back. Let's see, we are recording now, good. Okay, so he's got that. Okay, so what's next? I have just this morning posted an updated version of the book, and I will do that with dates. So either in the introductory section where I link the references, or well, and also on the current day's assignments or whatever, I will link any updated versions of the book with the date, so you'll know whether you have the most recent version or not. I've been doing some fairly heavy editing of the first part of the quantum field theory book because you guys have studied classical field theory, and you know a lot of it, or you had gauge theory last summer. So you know, if you've got those gauge theory book preliminaries down, I don't need to go over special relativity separately in the quantum field theory book, for example. There are some new things in quantum field theory about the Lorenz group that are not in the gauge theory book, and I'll talk about those specifically. The first thing I want to go into today, though, is having now looked at those first half dozen chapters of the gauge theory book, are there any parts of that that you'd like me to go over? You all dutifully did the assignment, right? You looked at those chapters. Okay, so you know we're talking about well, special relativity, of course. Oh, what else? Group theory, Lie groups, Lie algebras. What else did I talk about in there? Anyway, there are about half a dozen chapters, and you know, probably don't need the manifolds. Might be, was there one on complex numbers? You guys know what a complex number is. Don't need to review that, but I'll reiterate that assignment if you just forgot to do it.
Talk a little bit about the Hajj Dual.
Differential forms, that was one.
Yeah.
And yeah, Eli's rejoining us here. There we go. Welcome back, Eli. Yeah, still internet problems? Yeah, okay.
Good now.
All right, you know, I will, you know, as soon as the recordings are available, you know, they'll be there so you can catch up on anything you have to miss because of that. Okay, so the question now is with differential forms and specifically the Hajj Dual. But let me start with a quick overview of differential forms. Now, we're not going to use these a whole lot in quantum field theory. I use them more heavily when I do gauge theory, which of course, you know, we will do when we get to the standard model. But you know, mostly there we're dealing with one forms, and it's just a way to avoid writing a bunch of indices. Differential forms are coordinate invariant. So to see that, let's just look at a one form. Omega mu is some linear combination of some basis one forms. They don't have to be coordinate differentials. These you could choose an orthonormal basis. So I might write something like this, where these guys are orthonormal. And of course, that's a convenient basis for your vector space. So we often do that. But let's just look at the coordinate basis. And under a coordinate transformation, I know how to relate a new basis to an old basis because it's just the Jacobi matrix Vx beta. So what I need is for the components of any one form can have the opposite transformation property. So these in the y basis are going to be dx beta dy alpha omega beta. And then when you put these two together like this, these two are inverse matrices to one another and give you the same thing. So omega tilde mu dy mu. I think you guys can easily see that that's the same as omega mu dx mu. So when we work with differential forms, it's coordinate invariant notation. And the derivative and the Hajj Dual and the wedge product all respect that. So given, you good with this? Right. The chain rule tells you that if I multiply this by that, I get a Kronecker x something, and then it just changes the index. So to do differential equations, differential geometry in any dimension in a coordinate invariant way, we only need three objects: the D, the wedge, and the Hajj Dual. Now, D on any form just differentiates the components of the form. So we could have alpha, beta here. We could be starting with, well, I should have done the wedge first. A one form has a single dx. I'll always write it bold. I'll always write that basis with a bold D. Then I can form a two form by taking a wedge product of two one forms. And this is, if you want a formal definition, just take the outer product and anti-symmetrize it. But that's the only important property really that's the defining property of the wedge product, is if you interchange two one forms, you get a minus sign. This is nice because so much geometric information is contained in anti-symmetrizations. So if we can build up by taking multiple wedge products, P forms, right? A P form is going to be some linear combination of one forms. So we can put P of these things here. Those are supposed to be bold and X new, and we've got P of these. That's a general P form. I like to normalize them with a P factorial here because this is a totally anti-symmetric coefficient, and we're summing, P factorial, the same thing P factorial times because of that anti-symmetry. Now, in n dimensions, you can't anti-symmetrize more than n times. So you have one forms, two forms, three forms, all the way up to n forms. And up to an overall multiple, there's only one n form. And so you can make any n form proportional to a volume element. Now, if we look at what happens with the wedge product, if we take a P form and wedge it with a Q form, a different Q form here, something different. Okay, so what's that going to be? Well, in order to interchange the P form and a Q form, what I have to do is I move, this is like moving Q1 forms, or at least the basis forms, past P of those. So I move one of the basis forms of eta past P here. I'm going to get -1 to the P. But now I'm going to move all Q of these past. I'm going to get a sign that's P times Q. And then eta Q, I will have interchanged the whole set of basis forms. So interchanging a P form with a Q form, I get a sine minus 1 to the PQ. So if either of these is an even form, they just commute. If they're both odd, you get a minus sign. And it's that simple. Okay, that's pretty much all there is about the wedge product. Now let's move on to the exterior derivative. Then we'll get to the Hajj Dual question. Am I boring anybody? Okay, good. It's just all of you yawn broadly if I'm driving you nuts with repetitive stuff. Okay, so now if I take D of, let's say a P form, well, that's D of a, some coefficients. I probably have a P factorial omega alpha through beta dx alpha wedged with up to dx beta. And there are P of those. Now, there's only one function here. And we're going to prove the theorem, the Poincaré lemma, that applying D twice to anything gives 0. It doesn't matter what you let it act on. The point is you're going to be forming the anti-symmetric product of mixed second partial derivatives. And you're anti-symmetrizing a symmetric thing that gives 0. But we'll get there once I define it. This it's going to give D squared on these coordinate functions. That's 0. So it only acts on these coefficient functions, and it gives their derivative. So omega alpha, you guys okay if I denote a derivative with a comma? Okay, so, and then I put in another dx. And I wedge that with the basis that was already there. So this is a mapping. This is a mapping from P forms to P plus 1 forms. If you like that kind of notation for stuff. You guys have done a lot of math, right? So they probably write this sort of thing all the time. We can do that if you like, but having a rule for how you actually compute it is what to me is the most useful thing. So this is the exterior derivative of the P form omega. We pick up an extra down index, covariant index with the derivative, and we put in another basis form. So we've got a P plus 1 form here. Now, this includes a whole lot of familiar things. So if I have a function, right, it's just going to be the gradient of the function written as a 1 form. If I take D of a 1 form, I've got omega mu comma nu dx nu wedge dx mu. Be careful in the literature because some people will put this extra one at the other end, and that introduces a sign minus 1 to the P from my conventions. I was careful to use my conventions in the notes. You have to check if someone else uses a different thing. But now, look, this is anti-symmetric, so it kills any symmetric part of this derivative. Thanks, Nate. All that survives this double contraction is the anti-symmetric part of this, omega mu comma nu minus omega nu comma mu dx nu wedge dx mu. And you see we've written the components of the curl. Now, the curl in n dimensions, the curl is actually something that describes a plane. A 2 form describes a plane. All right, this is like the wedge product of 2 basis forms. It's determining an area, right? So this is a little infinitesimal area plaquette, and this is the generalization of the curl to any dimension you like. in 3 dimensions, there's only one direction normal to that. In higher dimensions, you've got n minus 2 directions orthogonal. So really what happens is the curls or cross products or things like that line a plane. It's safe to think of them as planar rather than reinterpreting the anti-symmetrized product as a vector in the normal direction. There is no unique normal direction in general. The reason you can do it in 3 dimensions is because the Hajj Dual takes 2 forms to 1 form, so you can map it back to a vector, right? That only happens in 3 dimensions. So now let's look higher. If we're in 3 dimensions, then we can take D of a 2 form, and that is going to be let's see. Well, we have omega mu nu dx mu dx nu, probably with a 1/2 factorial normalization, and we want D of that. So we're going to have a half omega mu nu comma alpha dx alpha dx mu dx nu. That totally anti-symmetrizes this object, right? The square brackets, are total anti-symmetrization. If I, if say this were 0, then if I explicitly anti-symmetrize these coefficients, then I can drop the basis and say, oh, the totally anti-symmetric part has to be 0. So, we can get back to normal differential equation type things that way if we like. Now, it turns out that this is very closely related to a divergence. But to get there, we need the third object, the Hajj Dual. The Hajj Dual is a mapping from P forms to n minus P forms, where n is the dimension. Right. In general, let me count. So I'm basically talking about the space of all P forms. I'm calling it lambda P. There's a nice book by Flanders that has all of this, by the way. How many degrees of freedom are there in anti-symmetric among P forms, right? How many independent components does a P form have? Well, the answer,
1/2 P times P minus 1 is my guess. But
what was your guess? That? Sorry.
Oh, binomial coefficient.
It's
No.
a binomial coefficient. Yeah, it's n choose P, right? You get to divide out redundancies, makes it just the combinatoric coefficient. So I'm going to choose P of n things, and then I'm going to choose. All right, I choose one of n things, then I choose 1 out of the remaining n minus 1. Then I choose 1 more out of the remaining n minus 2. So let's see. Why do I end? So is that what I end up with? And then the thing I end up with is redundant because all permutations of those P I chose, I divide out by P factorial. So I get n over n minus P different choices, and then the rearrangements of those I divide by another P. So I get the combinatoric factor. So let's look at how many there are altogether. And, it's, I can sum P equal 0 up to n and choose P, and that's 2 to the n. You know how to prove it?
Induction?
Binomial theorem. A plus b to the n is the sum from well, let's say k equals 0 to n of n choose k, a to the k, b to the n minus k. That's a handy formula in general. But now let a and b each equal 1. Over here we have 2 to the n, and here we just have the sum of these coefficients. So
Yeah, that's way better than induction, for sure.
yeah, it is. Yeah, that's true. All right. So I wish we could just go all afternoon with you guys, but yeah, not everybody can, so we won't. Okay. That's how many of these things there are, but you know there's a symmetry to these coefficients, right? So this coefficient is the same as n choose n minus b. So the Hajj Dual sets up a one-to-one onto mapping between the p forms and the n minus p forms. You're mapping from some subspace. So a p form you can think of as a p-dimensional subvolume of your n-dimensional space. And that's dual to some n minus p volumes. And that's what the Hajj Dual is doing. It's mapping you to that orthogonal space. So it's done using the Levi-Civita tensor. And for this, let me distinguish between the totally anti-symmetric symbol. So this is all, plus or minus 1 or 0. Totally anti-symmetric, and epsilon 1 to up to n is plus 1. If you're in space-time, it's usually 0 through 3 is 1. But I mean, you can define that how you like. And then totally anti-symmetric. I write the Levi-Civita tensor as it turns out that it's the determinant of the absolute value of the metric times epsilon alpha beta mu times the anti-symmetric symbol. It's got to be proportional to the anti-symmetric symbol, because every n times anti-symmetric object has to be proportional to that epsilon symbol. But the thing that dictates the square root of g, it's not actually necessary that it be this. It's necessary that it be an object of weight minus 1, where by weight, you can have objects that transform by some power of the Jacobian, where the Jacobian is the determinant of the coordinate transformation. And this is called a weight k field. All right, well, it turns out if you do a coordinate transformation on this, you pick up exactly one form of the determinant of the transformation matrix, because this anti-symmetrizes the components of that matrix, which is exactly what you do to form a determinant. So you put a dx dy on each index, and this is just going to give you the determinant of the Jacobian matrix, which is the Jacobian. So in order to form something that transforms as a tensor, you need to multiply by something that has the inverse weight. And it turns out the metric has twice the weight. It transforms as j to the minus 2. I think you can find this in Weinberg's relativity book. And so if you take the square root, it transforms with 1 over j. That offsets the j that you get from the volume element here. And so this transforms as a proper tensor. So depending on your coordinates, now you even need this in flat space if you're not using Cartesian coordinates. Cartesian coordinates, it's just 1. We just got a package. we get packages like every day. Make sure of that. So, all right, so those are the properties of this. Well, we want to work with the tensor. And we can use this to take the dual of things. So if I suppose I have a basis dx mu wedge dx nu, and I want to transform that. Let's see. Yeah, okay. Let's take the Hajj Dual of that thing. What we want is the basically the co-space. So what I can do is I can take epsilon mu nu, that matches my indices here. Then I can take all the rest and put a bunch of dx's on those. But now this is n minus 2 times redundant, so I'm going to divide this by n minus 2 factorial just to normalize. You can define that normalization any way you like. I define it that way. And so you see that because these indices are all different, the dx's that survive here are whatever two are not mu and nu. So this is some n minus 2 form in the volume orthogonal to the dx mu dx nu. You know, this could be dx1, dx2, and that could be, you know, dz, right? If this is dx and dy, I'd have an epsilon ijk dz over here, right? So that's how I map the components of the curl to a vector. Let's look at how that works. By the way, this is a great way to derive covariant divergence formulas and things like that, because all of these operations are, you know, they're coordinate invariant. So now let's see. Suppose I have a one form, and I take d of it, all right, in 3 dimensions. So I've got omega I comma j dx j wedge dx I. And now this is really a half of the antisymmetric part, and we recognize that as the components of the curl. Don't we? We do, don't we? I don't want to rush ahead here, but yeah, you know, a curl has components like dA y dx minus dA x dy. You know, things like this. That's just, and those are just anti-symmetrized derivatives. Those are the components of the curl. So, you know, z dy and y dz, or z xz and zx. So these are the components of the curl, but that's not the curl. What I can do, though, is I can take the Hajj dual of d omega 1. That's going to be a 1 form, because the Hajj dual takes a 2 form to an n minus 2 form, and in 3 dimensions, that's a 1 form. So what is this? Well, okay, so here's the rule. Take whatever coefficients you have here, and now raise them with the metric g I k g j l, and put the Levi-Chiguta tensor here, KLM. Then any extra indices, there's just one here, you saturate with the dx, or dx's wedged together. Now you count the number of these and divide by that factorial. So here it's already normalized. And then this is, well, what is that? You know, I could raise these. If we work in Cartesian coordinates, Euclidean space, those are just Kroneckers. But yeah, what this is epsilon, or omega I comma j and okay, if it's Euclidean, if G is just delta, then this is going to be the anti-symmetric symbol I, J, K, or M, let's call it, stick with M, dxm. And what I've done is to map this 2 form to a 1 form. And in fact, right, the components of the curl, of some vector, the kth component of the curl can be written as, this will be epsilon k l m dl of w m. That's one way in components to write the components of the curl. So up to normalization, well, the normalization's right here, but putting this dual has allowed me to map components that I know to be the curl to a vector. And so in certain dimensions, there's a real advantage to doing that. Sometimes you can gain stuff by going back and forth. There's a beautiful argument by Dirac where he does this with the electromagnetic field and is able to, by taking duals and choosing basis things, explicitly write the electromagnetic field in terms of 2 functions, the 2 real degrees of freedom of the electromagnetic field. A beautiful little argument, just, I don't know, shows up in some paper of his, I forget which. I stole it, I reproduced that argument in something I wrote, and if you want to see that, I could probably find it. It was a long time ago. Okay, so this is how we get from a 2 form to the curl using the Hajj dual. In general, let's look at the Hajj dual. We've got, let's take a P form, and we can write that as 1 over P factorial omega alpha through beta, P indices here, dx alpha, dx beta. Okay, that's the canonical way I like to write a P form. Now, if I take the dual of this, right, so here are my rules. Take the whole coefficient. You know, don't lose any differentiable bits of it. The P factorial is not going to matter. That's constant, but you want to take the derivative, omega alpha through, I'm sorry, no derivative. You want to raise all the indices with metrics. And, you know, if you're writing the divergence formula in general relativity, you know, you're going to want those metrics there. And then you have E mu through nu, and then rho through sigma, because epsilon always has n indices. And then you're going to put a dx rho through dx sigma out here. And now you have n minus p of those. So out here, leave space when you write this. You're going to put a 1 over n minus p factorial out front. And doing it this way keeps track of index positions correctly, keeps track of your usual normalization correctly. If you do this normalization and take a double dual, you'll come back to plus or minus the same thing. Depends on the dimension, you know, number of time dimensions, stuff like that. But basically, it will bring you back to where you started, which is, so it's what's it called? An involutive automorphism, if you like lots of syllables. I don't, not usually, but yeah, that's the name. Okay, so that's the dual. Using these 3 things, all of the tricks of the usual Boltzmann notation for vectors, the divergence, the curl, you know, dot product, cross product, all of those things are immediately generalized to n dimensions. So we can do all of those things with this. And I think I worked through in those notes examples of like the the divergence and the curl and so on. The cross product of two vectors, A cross B. All right, now, when I write something with a vector sign up here, what I mean is the contravariant vector. The kind relativists always define first, the tangent vectors, right? The vector space of tangent vectors to curves, right? If you're doing general relativity. Now, forms are every bit as good at vector space. Those are linear maps on curves in general relativity. You know, these arise independent, as long as you have functions and curves on a manifold, you can define two kinds of vector fields. Linear maps on curves and tangent vectors to curves. They're co-equal, you know. Forms don't think of forms as linear maps on vectors. You know, they are, you know, you can write it that way. You can also define vectors as linear maps on forms, but you know, they each have an independent and very nicely conjugate definition in terms of functions and curves. Let's not go off there today, but we lost somebody. Who did we lose? Guillermo. Ah, no, Kevin. Yeah, you moved up there. Welcome back, Kevin. So a cross product, if I write these as one forms, I'm going to make them bold, which I can't do on the board very well, but it's just the wedge product. All right, just gives me the anti-symmetrization of the components of these guys. So, you know, for all practical purposes, those are the same thing. The curl is of some vector v is 1-to-1 with d of a one-form v. In 3 dimensions, well, actually, let's look at star d star of a one form. Let's see what that is. That's a useful one too. In fact, it's useful enough that if people are doing lots of calculations with just a lot of formal stuff with forms, they give it a separate name, del, and call it the boundary operator. But if you're just, you know, doing general relativity or something, you know, it's the divergence. Okay, let's see what happens on a one form. So we're going to take star of d of star of omega alpha dx alpha. So first we're going to take star, just work from the inside out. So this is not hard. I'm going to allow myself, all right, there's going to be a g here, g alpha beta, and then an e beta. Okay, that's saturated. And then we have mu through nu dx mu through dx nu. Okay, well, how many of them? n-1. We started with a one form, so we've produced an n-1 form. Now we take d of that, and we have this 1 factorial. And I'm going to allow myself to call this omega up because it is. So I'm going to have omega beta up, comma, what happened I use? Let's see, well, I've gotten rid of alpha, so I'm going to use alpha dx alpha. That's how I take d, and that wedges with, well, let's see, hang on. I've still got my Levi-Civita here, mu through nu, and then I've got a dx alpha from the d, wedge dx mu, wedge dx nu. Those brand. Now I'm going to take the dual of that. Now this guy, that's an n form, right? We've maxed out a full volume element here. So when I take the dual of this, I have 1 over n-1 factorial. I have, let's see now, the full coefficient, omega beta comma, alpha, E, beta, mu through nu. Right now, that's the full coefficient. And so taking the dual of that, what I do is I put metrics on all the free indices, the alpha, mu through nu. So I'm going to have G, well, let me just raise the indices on the epsilon. Use the metrics the other way to raise indices. I'm going to have an alpha, mu through nu, and that's all of them, right? That is all of the that's all n indices. So there's no dx left. So I put 0 factorial and it's just 1. Okay.
Can we
Sorry?
get a board check, camera check,
Sorry. Thank you.
frame check? I think. Oh,
Okay.
maybe, yeah.
So, yeah. So there were going to be n metrics here, and I just used them to raise these indices. It's a tensor. I can do that. So now, look at what I've got. Star d star of a 1 form. I've got 1 over n minus 1 factorial. I've got an omega, beta, comma, alpha. And I've got 2 almost fully contracted epsilons. Epsilon beta mu through nu, or E alpha mu through nu. Those are contracted on all but one index. So, you know, if mu through nu are 1 through n minus 1, then they're 1 through n minus 1 here, and that one's got to be the nth index, right? Whatever's missing from the mu through nu list here is what beta has to be. Alpha's got to be the same thing. So this is proportional to a Kronecker. And let's put a proportionality in here. And that has to be what I get when I contract these 2 Levi-Civita tensors. Now, to figure out what lambda is, take one more contraction. So if I let beta equal to alpha, then here I have n factorial, possibly times a sign. If I'm in a PQ space with Q time-like directions and P space-like, I'm going to have a -1 to the Q, because in raising these indices, I've used Q minus signs. So there can be a sign here, but numerically it's n factorial. In space-time, there's a minus. Okay, on this side, that's got to be n times lambda. So lambda up to sign, I'll just write plus or minus, it's got to be n minus 1 factorial. And isn't that convenient, because we had that coefficient here. So star d star of omega, the n minus 1 cancels. We're going to get plus or minus. Now, what was this? I wasn't careful enough here. Way back here. This was the coefficient. When I'm taking d, I need to take comma alpha out here. And remember, this thing has a root g in it, times the anti-symmetric symbol. So this alpha derivative includes, you know, it's d alpha of root minus g omega beta. Sorry about that. Oversight on my part, but the n minus 1 factorial cancels. And now I have a Kronecker that makes this d alpha of root minus g omega alpha. And 1 over root g times that is the divergence theorem, right? From general relativity. I think, well, some proportion of you have seen that before. 1 over root g times the partial of root g times the vector is the divergent, the covariant divergence of the vector. Let me see now, where does the 1 over root g come in? It's sitting right here. Yeah, I made a bit of a muck of this. Sorry. The point is this is an epsilon. I have a coefficient here that's beta root G comma alpha. With an up index, we've convoluted in a determinant of the metric, and it comes in as 1 over root G times the Levi-Civita times the antisymmetric symbol. The antisymmetric symbol follows this numerologic thing. So I actually get exactly the divergence formula here up to a sign. So this is equal to the covariant divergence of a vector omega alpha. Yeah, so, sorry to lose that derivative. That was the importance I was trying to stress back here when I say take the whole functional coefficient. So the functional coefficient of this dx mu through dx nu is all of this stuff. So don't lose the derivative of functions that may be floating around in there, even if they don't have indices. Okay, so star d star is the covariant divergence. So let's see, does this help clarify or has it muddied the notion of the star, the Hajj dual? The Hajj dual takes you to the co-space.
It's done both, actually. So thank you. And I said it's done both, actually.
Oh,
but,
good.
Yeah.
Okay. Yeah. Yeah. So I worked through several examples in those notes. So maybe if you go back and look at those, you'll see some of these properties a little more clearly. And we can do more examples if you want. This is really handy stuff. This is how I like to find covariant expressions for things. But yeah, you've got to keep track of your root G's. Okay, so are there other questions? Okay, so the assignment for today was, chapters 1 through N of the gauge theory book as preliminary background kinds of stuff. So what can I help you with? Any of that before we see? Yeah, we've got a good 20 minutes yet. I haven't actually launched into today's lecture, but let's see. Okay, the book, I think you guys are probably quite comfortable with classical mechanics, Poisson brackets, that sort of thing. And anything you want to brush up on, chapter 1 of the quantum field theory book, summary of all last semester's class, everything you ever wanted to know about Poisson brackets, or most everything. Enough. So the next thing that I look into in the text, a couple things in special relativity that you may or may not know. Do you know the Lorenz invariant tensors? Do you know how many Lorenz invariant tensors there are? 2. The first is the definition of the Lorenz transformation. Which is, help me out guys, what's the definition of a Lorenz transformation? Bearing in mind that you guys are sophisticated field theorists, not undergraduate juniors. So you know that you can define it from the line element, invariance of the line element, right? Or boosts and rotations. But we know that we can act with Lorenz transformations on the Minkowski metric, and it gives us back the Minkowski metric because that's how we define these guys. We show that's equivalent to preserving the line element. Well, what is that if it's not a statement that eta is Lorenz invariant? Okay, so there's one. We're halfway. What's the other one? Okay, let's be in flat space-time here and Cartesian coordinates, so we don't have to worry about that. Any thoughts?
invariant into the Poincare group? Or invariant
Uh,
of Fourier
Lorenz,
transformation?
we're just looking for Lorenz here. Lorenz invariant. There's one more Lorenz invariant tensor, and it's not invariant under the discrete transformations. Just the proper isochronous Lorenz group. That's orthochronous. Proper orthochronous. Let's look at. Well, let's stick to space-time. Let's look at the transformation of the Levi-Civita. Now, the Levi-Civita tensor here, determinant of the Minkowski metric is just -1. We take the absolute value, so it's just 1. So in flat space-time and Cartesian coordinates, the Levi-Civita tensor is equal to the anti-symmetric symbol. So it's just a little simpler. So I need more indices: rho, lambda, nu, sigma, lambda, alpha, lambda, lambda, beta, tau. Now, this has to be anti-symmetric, right? We're taking the same matrix and acting on this anti-symmetric thing. It's going to give us an anti-symmetric thing over here, times perhaps some proportionality constant. Okay, well, we can figure out that proportionality constant by whacking all of this with another epsilon. This side, we're summing over 4 things, all permutations of 4 things. It's going to give us a 4 factorial and a sign, because raising this eta 0, 0 is -1. The rest are +1. So we're going to get -4 factorial times lambda over here. On this side, this gives us epsilon mu nu alpha beta epsilon rho sigma lambda tau lambda mu rho through lambda beta tau. This is just 4 factorial times the determinant of lambda up to a sign. Let's see, is that going to be? Yeah, odds are we get the sign here too. So what that means is that lambda is the determinant. Yeah, this is right, of your Lorenz transformation matrix. If we're working with the proper orthochronous Lorenz group, that's SO31, folks. That is unit determinant by definition. And this is equal to 1. And so here we have the Lorenz invariance of the Levi-Civita tensor. Now, under parity transformations or time reversal or chronicity, the determinant of the transformation could be -1. And then this transforms a pseudo tensor. But it's what would we say, pseudo invariant under Lorenz transformations. You know, it's invariant under SO31. Okay, so we have these 2 Lorenz invariant tensors. And let's see, I run through that. You know, these guys are related, because if I take 2, go here. If I take 2, you know, alpha beta epsilon rho sigma lambda tau, I can write this right now. The determinant gets squared, so this is truly a tensor. And in fact, each index here occurs over here. So I can always write this in terms of the metric. You know, I can write this as anti-symmetrized products of 4 etas. Only it's easier to write if I do it with deltas. So let me raise mu nu alpha beta epsilon rho sigma lambda tau is delta mu rho delta nu lambda or sigma delta alpha lambda delta beta tau. Totally anti-symmetrized one of those sets, and you have an identity. An identity like this holds in every dimension, right? A product of n Kronecker deltas anti-symmetrized. Now, taking traces of these things, you get some really useful identities that come up often. Remember when we were finding the divergence, I had a contraction of 2 epsilons over all but one pair of indices. I said it was a Kronecker delta. I'm basically using this identity. If I take contractions of this, I can get a whole series of nice identities. So epsilon mu nu alpha beta epsilon rho sigma lambda beta is proportional to 3 deltas anti-symmetrized. So mu nu alpha rho sigma lambda. Have you guys ever seen the multi-delta symbol? If you see a delta with multiple indices like this, it's the anti-symmetrized product of 3 deltas, 3 Kroneckers. You'll run into that once in a while. And let's see, what is the lambda here? I think this lambda is actually 1 in this case. If I contract 2 of these, all right, so these 2 are the same. So either mu equals rho or mu equals sigma, and nu's equal to the other one. So this could be delta mu rho, delta nu sigma, or it could be delta mu sigma, delta nu rho. But it has to be proportional to that. And if I set rho sigma equal to mu nu, I know I get -4 factorial over here. If I set rho sigma equal to mu nu, I get 4 times 4 is 16 minus, this becomes a single Kronecker, so 4, so I get 12 over here. And that tells me that the coefficient has to be -2. I did that fast. Did you get it? No, fair enough, fair enough. Okay, so I know that this contraction is proportional to the Kroneckers. You with me that far? Right, because yeah, one of these has to hold. They can't both hold. And now I know it's proportional, so there's some constant here. If I contract all of these indices with all of those, I know I get -4 factorial because there's one minus sign in space-time when I raise an index. So this symbol is minus that symbol. They're both totally anti-symmetric. So I get -4. Here, if I set rho equal to mu and sigma equal to nu, like I did over here, I get delta mu mu, delta nu nu minus delta mu nu, delta nu mu. Each of these is 4. This is a Kronecker delta mu mu if I just use one to replace the index on the other, so that's 4. This is 16 minus 4 is 12. You with me now? So the full contraction of this, setting rho sigma equal to mu nu, this side I get -4, this side I get 12. Any better? Almost a yes there. Okay, all right. So so this lambda, these have to balance. If I take a contraction of this, it's still got to be true. So to do that, -4 factorial, that's -24. I need a -2 here in order for the overall contractions to balance. If I take one more contraction of this, at epsilon mu nu alpha beta epsilon rho nu alpha beta. So I'm just going to set sigma equal to nu here. That's got to be -2. And then I'm setting, what did I set? I set sigma equal to nu. So that gives me 4 delta mu rho. Sigma equals nu minus delta mu rho. So that's just 3. So I get minus 6 delta mu rho. And then that'll check. If I trace this last one, I get minus 4 factorial. I trace this, I get minus 4 times the, I get 4 times the minus 6. Sorry. I'll say it again. If I trace the last index here, I get minus 4 factorial. If I trace the mu rho here, that's 4 times the minus 6, gives me minus 24 or minus 4 factorial. So that balances. So we have these various identities for converting any pair of Levi-Civita tensors into Kroneckers and or metrics. If you raise or lower indices on a Kronecker, you just get metrics. So, you know, you can write this all with metrics just as well. Just match up all the index positions and make it either delta or eta, just depending on what you need. Okay, so those identities are in the well, those are almost in the notes. I forgot the minus sign. I'll get the minus signs right. Let's see, in Euclidean space, there's no sign to worry about. But if we're in space-time, there's a sign. Yeah, I got to fix that. Make a note, fix that. Okay, now let's talk about discrete Lorenz transformations. You know, I mentioned the proper orthochronous Lorenz group, and that's because there are 2 discrete transformations in space-time. And these are significant when we talk about particle physics, because, you know, among the quantum numbers we can assign to particles are their parity and their how they behave under time reversal. There's a famous Cpt theorem. Under the combined operations of charge conjugation, parity transformation, and time reversal, you always come back to the same field configuration. And it's a very fundamental theorem in quantum field theory that it's hard to imagine it not being correct. It's that simple to prove, which means that when people see what's called CP violation in the decay of, say, the K meson or some of the higher ones they're making with tau quarks, not tau, but top and bottom quarks. You know, bottom mesons violate both charge and parity conjugation. So when you see a decay like this, that the parity reversed interaction doesn't happen at the same rate, and the complex conjugate relation doesn't happen at quite the same rate, so that even the combination C and P, both transformations are not preserved. And this is true of the K meson. Then the Cpt theorem implies that it's not the same under time reversal either, which means that particle production and antiparticle production are not equal for that particle, which has been invoked to try to explain why our universe is made up of more particles than antiparticles. You know, if at high energies we see enough of these CP violating particles, possibly we could understand the imbalance from that point of view. You know, it's an open question. People, you know, posit different things for why that might be, but we do see particles that violate combined CP. Okay, so what are these transformations? Parity is the usual parity transformation that you're familiar with. It just inverts the spatial coordinates. Now, you could ask, so you know, so we can write this as 1, minus 1, minus 1, minus 1. If we want to write it as a matrix, and it's going to invert the other coordinates as well. So like energy and momentum, the momentum goes to minus the momentum. There are pseudo vectors that don't go to minus themselves in the spatial part, and so those are odd under parity. Now, or I have to think about which is called odd and which is called even, but they're not like a normal parity transformation in any case. You could ask about a transformation that, say, just flips the x and y. You ever encountered one like that? If I take x and y and I flip it to y prime and x prime this way, so now I have new coordinate axes that run like this. You can see that this primed one is just a 180-degree rotation of that one. It is not a discrete transformation. It's part of the continuous rotation group. So anytime you take two of the spatial coordinates and interchange those, it's just a fancy rotation, a particular rotation. So parity is the only thing that happens among the spatial coordinates. Then time reversal, you know, ultimately requires a little bit of discussion, because the Newtonian version of time reversal is to just replace t by minus t, and that does the wrong thing. So we've introduced something called chronicity. So Newtonian time reversal, you just take t to minus t, and so your space-time thing is, you know, would go to minus t x, and that's a perfectly good notion of time reversal. But if you look at energy as a half mv squared, that just stays the same, and momentum mv, it's got one t in there, ddt, dxdt. I'm sorry, I'm p here. Goes to minus p. It's not just the time coordinate that's getting flipped. So you might be tempted to write a transformation matrix like this to do that, but that's not what happens here. Right, so you can define two things. So time reversal is a space-time transformation that in a Newtonian limit reduces to the Newtonian transformations, but that's not what we use. We use chronicity that reverses the time coordinate. Yeah, you know, I toyed around with several different ways to think about time reversal, like interchanging the past and future light cones. But if you've got a path that goes like this, then the time reverse path, you know, it's gonna start over here and track down this way. So if I don't know how to do this. I'm looking at myself in this. I got to reverse this mirror camera thing. But you know, if it starts off going this way, it's going to end up going that way. If you totally invert the path. So that's not quite what you want to do. You don't want to be shifting the positions. So, but reversing the time coordinate of all vectors is fine. Okay, that brings us to spinors, but it uses up all our time. So are you familiar with SO3 spinors? All right, you know, two component things under SU2. Right, it's in the notes in fair detail. Lorenz spinors are bigger. Those are Dirac spinors. And let's see, what do I say about those? We can talk about these in fair detail next time. I'm gonna want you guys to really understand spin, be really comfortable with that. So read what I've posted. You know, anytime in reading the quantum field theory book that I posted, that you start seeing every single equation numbered, you know that I wrote that part back when I was just learning LaTeX. And I was just copying and pasting a block of equations, and they were numbered. So everything has numbers in the old stuff. And you can tell from that just how old that really is. You know, that's, I don't know, I probably wrote the original book 15 years ago or something. I forget when. But I'm gradually working through and changing that. So in the sections that I've edited more recently, you won't see, you'll just see important equations numbered. That's one way to tell. And I will give a date and I'll tell you what I've done. So I can hang out for a while if anybody has more questions, or we can all go off and eat lunch or whatever you feel like.
Yeah, I'm going to lunch, but thank you.
Okay, I'll see you, Lyle. Have a good afternoon.
Yeah, I got to go teach labs myself. So
Eli, we should set up meetings. You know, I got to send you some supersymmetry stuff, and I'll let you
absolutely
correct it, because I don't know, I may have some times and stuff funny. And
all right,
I hope I've had a chance to read a little bit of it, and you can fix what I sent you. But I'll send you that. All right, see you guys soon.
All right,
we'll see it.
Okay.
I'm going to catch up on the reading. That's what I'll
Okay,
do.
great. I'll see you, Guillermo, Alex.
Yep, me too. Okay, see ya.
All right, bye now.
Bye, Professor.